Well, so you know, tonight's lecture about Mars is really going to get into some of the nitty-gritty of geology. So we need to review the rock cycle. And here are two students who are environmental science majors at the University of Texas who have prepared a short lecture that they now would like to deliver to us about the rock cycle. So let's welcome Shania and Mormay. Shania Mormay did that for an assignment in a class of mine, and privacy laws prevent me from telling you what grade they received for that assignment. A+. So please remember to silence your electronic devices. There's no conversations during the presentation. And we invite you to ask a question through our Slido app. So just go to this website, www.slido.com, type in HSCT number 113, and you could ask a question. You could start sending your questions in during the presentation if you like, or wait for the Q&A session. If you stay at the end of the Q&A, which will also include Q&A for our astronaut Dr. Jeanette Epps, there will be a raffle for door prizes and those tickets you got. Okay, so will we really live on Mars? Investigating the amazing red planet is going to be presented to us tonight by Joe Levy. Joe is a professor at Colgate University. He's a geologist and a planetary scientist. He first became interested in science, he tells me, when in the 3rd grade he had a teacher who made all science seem really cool. And then in middle school, he had a chemistry teacher who just blew stuff up a lot. He studied at the University of Chicago and then did his graduate work at Brown University. You know, geologists like Joe, we often describe, I'm a geologist as well, we often describe our research in terms of our field sites. So I would describe my research in terms of field sites in Texas, in the Caribbean, in Guam, in the Western Pacific Ocean. Here's how Joe's field areas are listed directly from this document. Quote, he focuses on permafrost land systems around the world and around the solar system, end quote. That about covers it. Joe integrates many fields of expertise, not just geology, but also biology and climatology. He's won a number of awards, not just for his research, but for his teaching as well. His research is often covered by the news media. We're very fortunate to have him here tonight. So please welcome Joe to the stage as he's about to take us around the world and around the solar system. Joe Levy.
Well, hello everybody, and thank you, Jay, and thank you all for coming. Who here wants to go to Mars someday? Okay, a lot of hands, that's good. I do too. I would love to. But before we go, we're going to need a plan. And so the plan that I want to talk with you about tonight is a little bit of science. What do we need to understand scientifically if we're going to explore the solar system? I want to talk to you about the most Mars-like place on Earth, Antarctica. And then finally, what are we going to do to put it all together and finally get people to Mars? So, I'm going to mute that. Jeanette, what's your plan? We just mute everything, the laptop. The alternative that Jay said was I could do a musical version of my talk, like the opener. And I said, for everyone's benefit, it's probably best that I don't sing. Okay, here we go. In a peaceful mode now. Close your eyes and imagine a red rocky ridge. If you can't imagine one, you could look at this one. It's being blown by a thin wind, dust and ice across the rock, and an explorer appears. She's wearing a life support suit, head to toe, thick gloves, heavy boots. She's wending her way through the boulders because it's only day 32 of a 90-day mission. And she's far from base, so if she tripped now, an injury could be catastrophic. She's carrying everything she needs with her in a heavy backpack. Food, fuel, water, electronics, science gear. Even containers for human waste, because this place is pristine. It's unaffected by humans, and a lot of science depends on keeping it that way. She finally gets to her target, takes out her tools. An electric drill whirs to life, and it cycles into the soil, and it bites in an icy layer below. She carefully pulls out the core, a length of soil and ice about the size of a big pencil, and slides it into a sterile cylinder. Her radio crackles. Radiation here is pretty bad. It messes with communications. It's base, and they want to know what's going on. She says, I'm on my way back, and I may have found something interesting. So this windswept rocky ridge isn't in Mars, it's on Earth. This is Beacon Valley, Antarctica. And our explorer isn't an astronaut, it's Jackie Gordial. She's a microbiologist. And what she's discovered is something almost as interesting as life on Mars. What she's discovered is a place on Earth that's so cold, so dry, so irradiated that there's no signs of life. There's a little bit of DNA in the soil, dead critters. But there's no RNA, evidence that living things are making proteins and living their lives. There's no ATP, the chemical fuel that cells burn in order to live their lives. So what I want to talk to you about today are a little bit about the limits of life on Earth in this strange corner of Antarctica. And the reason that I want to talk to you about Antarctica in a Mars talk is because if we understand how to explore and why to explore the most remote places on Earth, maybe that'll tell us something about how to explore one of the most remote places in the solar system. So the basic logic is if we want to explore here, we have to first learn how to explore here, Antarctica, Earth's southernmost continent. So how is Antarctica Mars-like? Well, parts of it aren't. Parts of it are covered by kilometers of ice. Parts of it at the coast are an ocean. They're teeming with whales and seals and penguins, all kinds of cute critters. But if you follow the transantarctic mountains, the ribs of Antarctica, across the continent, you'll eventually get to my corner of Antarctica, the McMurdo Dry Valleys. So everything that you see in this satellite image now is the McMurdo Dry Valleys of Antarctica. There's a lot of bright white ice, but what you'll also see is a lot of brown. And what that brown is rock and soil, permafrost, frozen ground. And where Jackie was working is up here in Beacon Valley. Now this is a hard place to make a living, but only that tiny little corner of Antarctica is truly not habitable. It's truly an environment too extreme for life. Everywhere else in orange here is just kind of a hard place to make a living. So I'd like to show you just how Mars-like Antarctica is. We'll leave McMurdo Station behind, kind of our landing site, our base, and fly into our next stop in Taylor Valley. So how Mars-like is Antarctica? Well, a cold day in Antarctica is like an average day on Mars, about minus 50 degrees Celsius. The dry valleys are a cold polar desert. The average annual temperature is around minus 20 degrees C, so freezer temperature. It gets 3 to 50 millimeters of precipitation a year, so that's like that much, all of which falls as snow. Did you catch a snowstorm? Unlike here, when it rains and the ground gets wet, all the snow that builds up in Antarctica sublimates away. It turns straight into a gas and goes right back to the atmosphere, so the soil is just as dry after the snow as it was beforehand. Antarctica is also windy. This is the shaky cam image from my tent up in Beacon Valley. And this is a wind-blown, dry desert. It's a freeze-dried continent. These winds are hurricane force and can blow dust and ice all around our sites. Antarctica is also salty. In fact, the saltiest natural body of water on Earth isn't in a pickle jar, it's Don Juan Pond. What little melt there is flows through the soil and picks up salts. It dissolves them and carries them down into the pond. The water then evaporates up. The water cycle works just as well in Antarctica as it does everywhere else. But the salts are left behind, forming this bathtub ring of bright white salt all around the pond. This pond may be beyond the salinity limits of life, even though there's plenty of water there. And Antarctica is irradiated by ultraviolet radiation coming from the sun. So the ozone hole is alive and well in Antarctica, and every summer, Earth's protective blanket of ozone disappears. That's the blues and purples here, and ultraviolet radiation streams down to the surface. So that's bad if you're an Antarctic researcher. It means wear a hat, wear a lot of sunblock. It's no different than being in Texas. But if you're a microbe, it means almost instant sterilization. This is a hard place to make a living. So based on these really harsh conditions, what do you think sets Antarctica apart amongst all the continents on the Earth? What makes it truly unique? I hear murmurs, it's cold. What else? I saw a hand. What is? One of 3 places where it's super cold. Antarctica, the Arctic, the ice cream store. Okay, so not unique, right? One of 3. To my mind, Antarctica is unique because it's the only continent on the Earth that doesn't have an indigenous population. There are no native Antarcticans. So the reason for that is because the environment is so harsh. It's so cold, it's so dry, it's so salty, it's so windy that there aren't enough resources for people to live there year-round. And what resources there are require a lot of technology, a lot of tools to pull out of the ground and use. So Antarctica is a recently settled continent, and it depends on a lifeline from beyond its borders for people to work there. So what do you want to do if you want to explore Antarctica, this barren alien place? You need 4 things. You need a reason to go, science. You need consumables, food, fuel, water. You need hardware, the tools of exploration, a ship, a building, a lab. And finally, you need political will. So let's talk about those. Let's get all those resources together to explore Antarctica. The reason to go. Antarctica is a continent set aside for science. So the Antarctic motto is eat, sleep, science. It's a great place to work. That's all you do for months at a time. So Antarctica is famous for its climate science. In fact, the primary reason scientists go is to drill down ice cores to extract a record of Earth's climate over the last 1 million to 500 million years. Those records are stored in ice cores that are drilled up from the ice cap. And by looking at the composition of the ice and the bubbles inside of the ice, we can reconstruct the conditions in Antarctica through ice ages, through geological time. Antarctica is also a great place to be a biologist. These are our emperor penguins and a crab-eater seal, maybe a Weddell seal, not a biologist. Antarctic macrofauna is very charismatic, big critters, but Antarctic microfauna tell us something about how to survive near the limits of life, in some place that's too cold and too salty for almost anything else to live. All these pictures show bright Antarctic sunshine, but Antarctica is also a great place for astronomy, because half the year, being below the polar circle, or the Antarctic circle, Antarctica is in night. So telescopes can look further into space, further back into time in Antarctica than almost anywhere on Earth. And the viewing conditions are spectacular. No light pollution, no air pollution, clear skies. But the science I want to tell you about is in the dry valleys. In particular, up in Beacon Valley, near that limit of life point. What excites me about Beacon Valley is this red stuff. That's a glacier. Now, Joe, you say, glaciers are made out of ice. They're not red unless it's a snow cone. What I'd like to call your attention to is the ice accumulating up here in the mountain peak. It piles up and starts flowing down through the valley. Rocks and sand get dumped on the glacier, and as the ice flows, it gets progressively covered by that debris. As the ice sublimates away, it leaves the debris behind. And what happens is a blanket of rock and soil build up on top of the glacier, protecting it over time. It doesn't sublimate away. It doesn't melt. It's right there underneath the blanket of dirt. And so the oldest ice on Earth is actually hidden here in Beacon Valley, and it's 8 million years old, protected by this debris blanket. So we'll get back to that. Another thing I'd like to tell you about is in Taylor Valley. This is work I did as a postdoc, and I love it. So I told you Antarctica is a place where very little melting happens. It's sublimation dominated. But snowbanks at the height of Antarctic summer can melt. That water can trickle down into the soil and then flow down into these ponds. This is like when you turn on your hose and water soaks into the ground. It darkens the soil and expands out from wherever you're watering your rose bush. These briny water tracks, those dark lines coming down the side of the valley wall, teem with microbial life. In fact, these are Antarctic oases, places where microbes and algae can thrive even in the midst of this extremely cold, dry, harsh desert. So that's our reason for going, science. What about political will? Well, Antarctica is a preserve. It's set aside for science, but that hasn't always been the case. During the heroic age of exploration in the 1800s, different nations explored different parts of the Antarctic coast, and they said, if I'm going to explore this sector of Antarctica, like a pie slice, I'm going to claim the land all the way to the South Pole. So the United Kingdom, Chile, France, New Zealand, everyone has little pie slice sectors that they claim, except for this, let's see, where's our unclaimed sector? In here. So if anyone has a boat and a flag, go, quick, I won't mind. 1958 rolls around and the United States decides that Antarctica really needs to be an international science preserve. And so, like the guy who opens up the pizza box and sees the pepperoni in the middle and pulls it off, and that's everybody's pepperoni he just took, the US built a station at the South Pole and said, hey, where these pie slices come together, that's our base. So we don't recognize any territorial claims. much of the political will in Antarctica, much of the political maneuvering is to support South Pole Station. And the way South Pole gets supported is through McMurdo, our logistics hub for Antarctica. So we'll take a quick look at McMurdo. McMurdo is located next to the Dry Valley, so it's a little town I spend a lot of time in. It's out here on the end of the Hut Point Peninsula on Ross Island, home to an active volcano or two. It's not an evil lair, I promise. We'll zoom in and you start seeing kind of evidence of signs of life. You know, X marks the spot, right? What's that? That's an airfield carved into the sea ice outside of McMurdo Station. We'll zoom in again, and you start seeing the shapes of a base starting to take shape, tucked against the rocks. We'll zoom in again, those are some fuel drums, and now you start to see McMurdo, a tidy little research station and home to the hardware that we need for scientific exploration. So here's McMurdo, a lovely little town, about 1,000 people. It has everything you might need to eat, sleep, and science. So it has a dining hall. It has some dormitories. It has a lovely lab. It also has a pretty good coffee shop. You can get an espresso. It's no Starbucks. And a couple of bars. And it also has all the other hardware you might need for exploration. It has machine shops and skidoo, snow machine repair facilities, and a helicopter pad. And this is where all of Antarctica's cargo, all of the hardware comes through. So how does it get there? Well, me and my scientific gear might leave upstate New York, Colgate University, and we'd fly to Los Angeles. From Los Angeles, we'd fly to Sydney, Australia. From Sydney, Australia to Christchurch, New Zealand. From Christchurch, New Zealand, we get on an Air National Guard military transport plane and fly to Antarctica, to McMurdo Airfield. If we're lucky, we get to fly on one of these. That's a C-17. It's a jet-powered, giant flying warehouse. If we're not lucky, we end up on a Herc, a C-130. This is a rattling propeller-powered airplane that takes what should be about a 5-hour flight and turns it into an 11 to 16-hour odyssey. But you finally make it, you land on skis, and there you are in Antarctica. Now, that brings mostly the people and the high-priority gear. But what about all of the stuff that people need for exploration? Well, the Antarctic program moves about 40 million pounds of cargo every year, and so most of it comes on this big boat. So what is that? That could be a helicopter, steel for building, nuts and bolts, food, gas, toilet paper. Antarctica is being explored by people, and it all comes on this boat. But the real fun for me and the real exploration doesn't happen in McMurdo. It happens in the dry valleys. So how do we get there? Well, you leave McMurdo and hop on a commuter flight. What's that? To head to the dry valleys, it's a helicopter. So it might seem like a really glamorous way to fly around until one starts landing on you in the middle of the field, and I think I'm still getting dust out of my ears from this landing. So all of our gear has to get picked up and flown out to our field sites so we can explore and do our science. Yeah, it's rough. Sandstorm. All of our gear has to be portable, like gear that will be used to explore Mars. So it has to be packed up in McMurdo, it has to be lightweight, it has to be able to be set up by a bunch of sped-up clowns, my field team, and it has to be optimized for use. It has to survive in this harsh environment. Then you make a house a home by filling it with all of the consumables that you might need for exploration. So here's our food and our Pringles stash. Here's some propane for our stove. There's electrical power systems for our communications devices. Everything that we eat in Antarctica has to come with us from outside. The consumables don't come locally. The one resource that we do have in abundance, though, is solar power. This is 24 hours in Beacon Valley, and during the summer when I work in Antarctica, it's light all the time. So take a look at this. The shadows are marching around the tents, but the sky never changes color. It's bright, 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 bright. It means if you want to eat, sleep, and science, you could even cut out the sleep part. You could just eat in science. The other resource that we have in abundance that gives us a real advantage over future Martian explorers is ice right at the surface. We can go outside with a snow shovel, dig up a pile of snow, and dump it right in the pot. It doesn't thaw quite this quick. That's about an hour of propane burning. But we have water available for drinking, for washing, for cleaning. We also have one other resource that future Mars explorers aren't going to have in abundance, and that's air. We take it so much for granted that we don't have to bring our air with us. We can just breathe beautiful, clean Antarctic air. So before you think that it's totally paradise, I just want to show you how all these consumables come together. This is taco night in Beacon Valley. That's some ice at the end of some refried beans. It makes you miss Torchy's. It really makes you miss Torchy's. So, not the most glamorous of culinary scene. So if you want to explore Antarctica, you're going to need a reason to go. Science. This is a continent set aside for science. You need hardware, and we have it in spades. We have McMurdo Station, our logistics hub. We have the helicopters. We have the tents. We have the stoves. We have our scientific gear. You'll need consumables, food, propane, some kind of power system, maybe some gasoline for your generator. And you'll need political will, which we have, because the US Antarctic program is behind us 100%. So what about Mars? Do we need those things? And more importantly, do we have them? And I'd like to suggest to you that the answer is probably yes. I've also, though, forgotten one important resource. Matt Damon insisted that we say that we need potatoes. So I'll add a fifth item to the list, but I won't get to talk about too much about where to grow them. So how do we explore Mars? How do we make sure that we have these resources? And the first resource we need is a reason to go, science. So why go to Mars? Because it's there is an answer that I bet everyone in this room would say, that's why we should go. But what are we going to tell taxpayers? What are we going to tell our fellow humans? And the real reason to go to Mars, scientifically, is to understand how planets begin. On Earth, most of the record of Earth's history has been destroyed. Earth is an energetic planet with volcanoes and plate tectonics. The crust that we heard about so beautifully, it's constantly being recycled. And so most of it is gone. If we want to understand how planets evolve, and importantly, how planets shape the life that evolves on them, we need to look back in time. So imagine, if you will, if everyone wants to get out their geological time scale, it's like this, your arm. The Earth accretes out of dust and ice at your shoulder 4.5 billion years ago. If you follow geological time forwards, most of the animals that we're used to thinking about, the big multi-celled organisms, were born. Let me put this clicker away while I gesture wildly. That was even worse. Just going to put this down. Earth begins at your shoulder. Most of our life starts at the Cambrian explosion 500-odd million years ago at your first knuckle. Along the way, life gets its start somewhere in your forearm. We don't really know for sure, and scientists are always pushing back when the earliest life on Earth was, but it's mostly lost in your bicep. Dinosaurs walked the Earth around your second knuckle, and humans, that tiny dot at the end, are less than last night's fingernail growth. We want to understand this whole history. We want to understand how cataclysms like meteorite impacts that wipe out the dinosaurs on your finger, it's a small meteorite, pow, how those come into being. We want to understand how planets evolve, and to do that, we can't rely on Earth. The record is gone. It's been reworked. The history book has had the pages torn out by geological processes. So that's why we go to Mars. Because Mars has the whole arm written right at the surface. A planet that doesn't have plate tectonics, that isn't constantly churning itself over, builds up its history over time, layer by layer at the surface, and we can read it if we go there. So future astronauts are going to bring the arm home to us. What are the highlights of Martian science? Well, some are in the past. Some are that early part of planetary evolution, when planets first start forming, when life first starts arising. And that's displayed at the surface in places like this, Jezero Crater, one of the 2 finalists for the Mars 2020 rover to land. Mars was wetter in the past, wet enough that water could stream down through channels and out into standing lakes in craters, forming deltas like this. It's not as big as the Mississippi River Delta, but it's an incredible delta nonetheless, because it's made out of carbonate minerals, as discovered by researchers here at UT Austin. And where there are carbonate minerals, it means there was standing water. It also has clay minerals. Clay in the soil here is not great for your foundation, but it's a sign that there's water interacting with the rock, weathering it, changing it. And those clays are also found in this delta. So this ancient Mars tells us something about how habitable, how pleasant for life Mars was in its ancient past. Mars is also really interesting today. These are recurring slope lineae, and they're active right now. We're looking at the edge of a cliff on a Martian crater, and every Martian summer, these dark lines come racing down the edge of the cliff. Then in winter, they disappear. The next year, they flow down again and disappear. This should look familiar. This should look a lot like Taylor Valley. So people think that these recurring slope lineae on Mars, geologists give terrible names to things. They're lines that recur on a slope, recurring slope lineae. Poetry. Scientists think that these recurring slope lineae are brine channels, salty water that's trickling down like water from your garden hose through the Martian soil. And that's a good place to search for modern life, things living in these wet soils. The problem is getting to Mars is really, really, really hard. If we're going to explore it, it's going to take a lot of work. And I just want to tell you what the stakes here are. Human explorers are going to have to deal with a Mars mission exploration history that is fraught with failure. Starting in the 60s, these are all of the missions that have been sent to Mars. Red is from Russia, blue is from the United States, yellow and pink are from international partners. And all of the missions that don't make it end up here. Only about 1 in 3 missions sent to Mars historically have made it into Martian orbit, to fly by successfully, or to land. This is a hard thing to do. What makes it hard for humans? Being in space. Turns out stopping is the hardest thing. So to get to Mars, you have to leave Earth behind. That's the nice blue dot here. There's lots of ways to get to Mars, but the best comes every 2 years when Earth and Mars line up so that you can launch yourself with the minimum amount of fuel needed from Earth, get on the fast train to Mars, and get captured by Mars's gravity with the minimum amount of fuel you need. The reason you want to minimize that fuel is the more fuel you have to bring with you, the heavier your spacecraft. The heavier your spacecraft, the more fuel you have to bring with you. The more fuel you bring with you, the heavier your spacecraft. You might notice how this goes. Every kilogram of fuel that you bring is 1 less kilogram of food, water, air, or toilet paper. So this is important for Martian explorers. You could go faster, in which case you'd need to bring more fuel. That's right out. You could go slower, but then you would expose astronauts to the space environment for longer. They would be exposed to radiation more, to micrometeorites more. Astronauts, you might think of them as people who like to go to space, but I bet most astronauts going to Mars would rather be on Mars than on their way to Mars. So you have to get there, you have to stop, and not too abruptly. Thanks, Elon. So how does stopping not too abruptly work? Well, imagine it's the 2030s. The human mission is on its way to Mars. Morning begins on Mars like any other. The wind is blowing, it's cold, there's a red rocky ridge. But then a new shooting star appears in the sky. And that shooting star is our human mission to Mars. What it's doing is taking advantage of Mars's thin atmosphere. Mars's atmosphere is only about 1% the thickness of Earth's, but it's enough that you can use it to slow down the friction of heat between the spacecraft and the atmosphere, slows it down. Just enough that you can send out a tiny little drogue parachute, and that tiny little parachute can pull out a bigger parachute. Parachutes aren't good for delivering anything to the surface of Mars that's much bigger than a toaster. So we're going to need something else to get down to the ground. Some rovers use balloons and airbags and bounce. That's not good for astronauts. So human missions are probably going to need rockets, retro rockets. So there's one last burn before we make it to the ground safely. Will they? Won't they? Oh, it's too much of a cliffhanger. I have to go on. It turns out this is a really hard thing to do. And it doesn't always happen successfully. This is the remains of the Schiaparelli lander, part of the European Space Agency's mission to Mars. Schiaparelli was supposed to be a lander. Schiaparelli turned into a crater. So this is a before and after. Here's a big crater. This is before and after. Before and after. Here's that white dot is the heat shield from the Schiaparelli lander. That worked. It slowed down in the atmosphere. That black dot is the crater. That's the lander. The radar spoofed. It didn't know how high above the surface it was, and the rockets fired when it was -2 meters, not +2 meters. That's a problem. So how do you avoid this problem? Well, you pick a safe landing place. You might think that there's a whole surface of Mars to explore. It has the land area about the same on the whole planet as Earth's land area. So think of Earth minus the oceans. That's a lot of place to explore. That's great. But the engineers say there's some rules. Rule number 1, equatorial. Only between plus or minus 30 degrees of latitude. So if you don't have your globe with you, everyone brought their globe today, right? Okay, if you didn't bring your globe, that's Austin to Buenos Aires. That's the window of Earth's middle that you could land a spacecraft on. Same window for Mars. And the reason for that is we want nice temperatures, not too hot, not too cold. We don't want a lot of temperature change. We don't want a lot of fuel to change the orbit and actually land there. You also need to pick a place that's not too high and not too low. Too high and there's not enough atmosphere for those parachutes to begin slowing you down. Too low and there's too much atmosphere. That's out. It can't be too steep. You don't want to hit the surface and roll. It can't be too dusty. Mars is covered in dust. Why wouldn't you want dust? Well, dust gets kicked up when you land. Dust gets into your spacesuit seals. Dust gets on your solar panels. Dust gets everywhere. That's the Antarctic experience. Dust is dangerous for missions. It can destroy electronics. It can keep seals from sealing so the air leaks out. Dust is a disaster waiting to happen. But it also can't be too rocky, because you don't want to land with those retro rockets firing and then hang up on a rock. That's bad, because then your rocket tips over. It also can't be too shiny. It can't be too dull. That'll spoof the radar. And so what we're left with in the color coding here is, I don't want to say boring Mars, but it's average Mars. There's a little bit of the yellow and red highlands here. There's a couple of interesting crater basins, but it's not the whole planet. But at least it's a safe place to land. So we made it. That's the cliffhanger is resolved. Now what? Well, we need to go through our checklist for resources. We have our reason to go, that incredible science, ancient, habitable Mars, modern, wet, salty Mars. We have our hardware. We've landed our lander. If we were really lucky, we might have sent 2. Maybe one is waiting for us for the return trip home. I would much rather go to Mars if I knew my ride was waiting for me. It's a long way for an Uber, but the price is right. So what about consumables? What are humans going to need to live on Mars? And the ultimate consumable is H2O, water. Water is awesome. Water is essential. We live on a water planet. We're mostly made out of water. The big problem with water is that it's heavy. You remember what I said about rocket fuel? The more fuel you bring, the bigger the rocket. The more fuel, the bigger the rocket. Water's kind of the same way. If you have to bring your own water with you, that means 1 less kilogram of science. It means 1 less kilogram of toilet paper. I want these astronauts to be comfortable. That should be a key point. So what are we going to do? We need this water. We need water to break it apart into hydrogen and oxygen so we can breathe the oxygen. We can make our air. We need water because our astronauts are going to want to drink when they're at the end of a long day. We're going to need water because you can break the oxygen apart from the hydrogen and then recombine it. And when you recombine it, it's kind of like my 6th grade science teacher. That's an energetic reaction. So you can build your own rocket fuel if you have enough water and enough electricity to break it apart and then let thermodynamics do their thing and bring it back together. So where are they going to get the water? Well, future Martians are going to have to live off the land in the same way that Antarctic explorers live off the land. This is essential. If humans had to rely on bringing all of their resources with them, we wouldn't be able to explore very far. In fact, if you can imagine you're a pioneer setting off from Independence, Missouri, settling the American West. You have your mule team with you, you have your Conestoga wagon behind you, and you have your hay, food, your fuel. You have your water for the mules, that's in a big drum, and you have your air, and I don't know how much a mule breathes, but it's a fair amount. It turns out if you have to bring all of this with you, your mules are mostly pulling their own food, water, and air. They're not pulling the nails that you're going to need to build your house. They're not pulling the cloth you're going to need to make your clothes. And we only would have progressed about 100 miles beyond Independence, Missouri. Now, as every Texan knows, there's a lot more than 100 miles west of the Mississippi. So what are these explorers going to do? They're going to live off the land. And it turns out Mars has a lot of water. You just need to know where to look for it. We've caught Mars at a really boring time in its history. Between 2 million years ago and about 500,000 years ago, there was an ice age on Mars. Ice from the polar caps spread out to cover the surface, like cream cheese on a bagel. So there was a huge pile of ice that got smeared out, and some of it is still there today. Now, Mars's orbit has shifted. Much of that ice has gone back to the poles, but some of it is still hiding. What does Antarctica tell us about where to find ice that's hiding? Look under the dirt. So this is a view from the HiRISE camera, our best satellite sensor orbiting Mars today. You can see 25 centimeters for every pixel. So HiRISE can identify these chairs. HiRISE, if we took the roof off, could identify people here, probably by hair color. It's an incredible camera. And what does it see? Well, it's just like Beacon Valley. It sees debris scattered across the Martian plains, red, boring rocks, can't drink that. It sees more red debris. But in between, there's a cliff. There's our cliff face. And what it sees when it looks in is bright, blue, shiny ice. Now, this is a lot of water to drink. The good news is this ice is everywhere. So here's our view of Mars. Here's the equator. Here's the pole. Bluish, cool colors here represent the percentage of ice in the subsurface, in the upper meter or so of the soil. And what you should notice is that's a lot of ice, more than a third in many places. That's ice you could go scoop up and put right in the pot. The problem is it ends at about 60 degrees latitude, north and south. That's polar. What did I tell you landing criteria were? Plus or minus, 30. So this ice is a little bit far away. So it's a case of water, water everywhere, but not a drop to put in the bucket and thaw. What about this weird blue stuff? Well, that's equatorial. That might be good. It turns out that weird blue stuff there are hydrated minerals. Mars is a rocky planet, go figure. And in places that rock has cracked. Where water has flowed through that rock, in the same way water flows through the karst here in Texas, it sometimes dissolves and sometimes leaves minerals behind. These minerals have water in them. They're minerals that you've heard of before. Quartz can be hydrated. Sulfur-containing minerals can be hydrated, like jarosite. Everyone's heard of jarosite right now. But gypsum, maybe you have. So within the rock, cracks can fill up with hydrated minerals, minerals that have water stuck to them. So what do? What's a recipe for water on Mars? Take one rock, check, bake at around 350 degrees C for 1 hour. What comes out is not brownies. What comes out is the water. It boils off the rock, and you could, in principle, catch it in a collector. So you really could drink the rocks on Mars. So pros for drinking rocks. They're equatorial. They're abundant. We know they're there. Cons, it's a hard sell. No one on Earth drinks rocks. This is an unproven technology. So this is a real point where future engineers can develop and contribute to Mars exploration. So what are we going to do? How are we going to save our astronauts and get them the water they need? Well, one answer comes from debris-covered glaciers. This is a view of a mountain on Mars, and it has this funny-looking apron around it. It turns out that these are debris-covered glaciers, discovered in large part by researchers right here at UT Austin. When you fly an orbiting radar named Charade over these, the radar shoots radar pulses into the ground. Some of them bounce off the surface. Some of them make it through. And when they see a subsurface reflector like this, a bright area where the radar waves come bouncing up, it's possible to determine the composition of these funny landforms. And they're very nearly 100% pure ice, kilometers long. These are giant ice cubes. Some of them reach down towards 30 degrees. This is a huge pile of ice. How big is it? If you took all the debris-covered glaciers on Mars and melted them out, it would cover the Martian surface with a layer of water deeper than I am tall. It's the deep end of the pool, about 2 meters. There's a lot of water here for future explorers. This water also helps the astronauts in another way. The Martian environment is not a safe place to live. It is bathed in radiation. It makes that ozone hole look pretty benign. So many people think that the first Martian explorers are not going to get a room with a view. That's a bummer. There's a lot of good vistas on Mars. They may have to live underground to protect themselves from radiation, from micrometeorites, from all the things that could really do in a mission in a bad way. And so many people think that you would just bring a backhoe to Mars and burrow. But I'd like to propose something a little bit more radical. If you have this debris-covered glacier, and you've brought in a giant drill to bring out the ice cubes, and you're drinking that water and toasting your success as an early Mars explorer, I say, why not go into the glacier? Why not live in the ice? This is not such far-fetched science fiction. This is the International Seed Repository on Svalbard, an Arctic island, other end of the planet from Antarctica. It's a tunnel bored into solid, ice-rich permafrost, frozen ground. It's a great place to visit. There's tons of parking. It's more interesting on the inside, though, than it is on the outside. It's a giant tunnel. It's protected from radiation by the water around it, by the frozen water, the ice. That's why it's being used to store seeds. Humans are experts at burrowing into ice. In fact, it's something that we've done in the US, too. This is the Fox permafrost tunnel in Alaska, built by the Army Corps of Engineers. This is all ice-rich, frozen ground. Now, in Alaska, there's plenty of water. They didn't have to drink it. But each one of these shiny patches of ice in the tunnel is a potential water resource for future explorers. So I'd like to think that debris-covered glaciers on Mars might be the answer to all of our consumable problems, and also the answer to some critical needs for shelter. And if you don't like the size of your bunk, you could always take a shovel or a chainsaw and just dig it out, make it a little bit bigger. So ice solves a lot of problems. So do we have everything we need? We have our reason to go, science. We have our hardware, our spacecraft. Thanks to the water on Mars, we mostly have our consumables. A little bit of food, maybe a little bit of propane, probably some Pringles, if I'm going. What about political will? Going to Mars is expensive. Going to Mars takes a lot of resources, on the order of billions of dollars of resources. And that's a lot to ask from taxpayers. There are problems on Earth. Couldn't that money be spent better here? That's a decision that everyone has to grapple with. But I think everyone in this room is passionate about exploration, is passionate about making Earth a multi-planet species. And so my hope is that the people in this room who can vote will vote, and will select leaders who will organize the political will needed to send humans to Mars. And for the people here who can't vote yet, I hope that you become those leaders, because the people in this room, I think, have the power and the capability to make the decision to send humans to the red planet. So I'd like to close back in Beacon Valley, back at the limits of life, because Jackie's Valley, where nothing lived, where it was too salty and too cold and too dry, too irradiated, is just around the corner from my field site. So you walk down the valley, cross to the other side, hike up a big red rocky ridge. And the wind blows, dust and snow, and another explorer, actually two of us, me and one of my undergrad students, appear over the ridge. And what did we find in our end of the valley? A landscape a lot like that barren one, that one where nothing could live. But what sets this part of the valley apart is a tiny little snowbank. That snowbank, at the height of summer, when the sun is most intense, melts for a few days a year. That water flows down the valley wall, a salty, briny water track, and it pools at the bottom of the valley. And what I found when we climbed up into this valley knocked my socks off. This little frozen pond, barely the size of these chairs, was surrounded by a thick mat of bright orange extremophile algae. This is a living thing that has defied the odds. It's defied the salt, the lack of water, the radiation, the wind, and the cold, and it's eking out an existence right at the border of the limits of life on Earth. And so I sampled it, and I headed back to McMurdo Station, a pretty happy camper. This organism is my role model. It's overcome the Antarctic environment, and it doesn't just live there, it thrives there. And so I like to think, to answer this question of, will we ever live on Mars, if that algae has its way, and if we're as cool as it, the answer is going to be yes. So with that, thank you all so much, and I'd love to take any questions.
Awesome, Joe. Have a seat here. Sure. Wow, thank you, Joe. Let's put the Slido address up there. slido.com. HSCT_113. So, wow, pretty awesome stuff to think about. And there's a lot of really insightful questions here. Why don't we start with a question, how would you stay on Mars with no oxygen? One tank won't be enough for a while, and it would be hard wearing a suit full of oxygen masks. This comes from Wolf Like Duck, is the person's name.
Wolf Like Duck, that is a great question. The consumable problem is something that I talked about. How do you bring these things that you need, air and water and food, with you? And so half the battle is making the air. And for that, we have this abundant ice. We can break apart the hydrogen and the oxygen with electricity, with solar panels, and then you have the oxygen. But then you're right, you just have this one tank. And who's ever been for a hike wearing a scuba tank? That's not really a thing, that's exhausting. You wouldn't have a lot of air. So future explorers are going to spend some of their time outside of their vehicles with a life support system, but hopefully they'll also have a pressurized rover. So what's that? It's an RV with an airlock. See if you can get one of those outside of town. It would be a mobile habitat, so you could explore the surface and then only go outside when you saw something you really needed to collect, a rock or a water track or a recurring slope lineae brine puddle. So hopefully we'll just bring our air with us, at least for the time being.
Excellent. So water on Mars, probably because when the snow melts, water should be created. But how does the water disappear if there's no water cycle or weather in space?
Wow. Oh, another great question. So this is getting at those recurring slope lineae, those fingers of dark, wet soil that come down the valley walls. If you know the answer for how those form and disappear every year and then reform, you have a Nature or Science publication and a big prize waiting for you. That is a giant unknown. I wanted to bring some science to this talk that's totally unsettled. We just don't know where that water comes from. Does it come from melting snow? Does it come from salt sucking water out of the atmosphere? It's unknown. So if you have ideas about how to explore it, grab some high-rise images. They're on the internet. They're easy to download, and take a look and see what makes sense to you.
Great. There's a lot of questions about Antarctica, including can I take a family vacation to Antarctica? How can I get a job in Antarctica?
Two great questions, and both are actually pretty easy. Antarctica is a continent set aside for science, but protecting it means having people who love Antarctica. It means having people who will vote for leaders who will protect Antarctica, and the way to do that is by bringing people to Antarctica. So there are tour operators who will take you in a boat or a plane to the Antarctic Peninsula, where you can see penguins and whales and icebergs. There are even boats that come into the Ross Sea, where I work, near McMurdo. And there's even some that will helicopter you in to the dry valleys. There is a visitor zone. There's no concession stand and no restroom facilities, but it's an incredible experience to land there. So you can go. If you want a job in Antarctica, you could become an Antarctic scientist, highly recommended. Then you get to come and talk to you all. But there's also 1,000 people at McMurdo every summer, and most of them aren't scientists. Most of them are construction workers or galley cooks or lab managers. So there's a huge infrastructure to support science, and that's you can look at the U.S. Antarctic Program website and the contractor who supplies the personnel and the facilities, and yeah, apply. It's a great place to spend a season.
And we need bartenders too.
Yes, they are volunteers.
Volunteer bartenders, okay. Well, at this point, why don't we bring out Dr. Jeanette Epps, the NASA program. Welcome her to the stage. Here you go. So, Jeanette, you're in the NASA Astronaut program. You've worked for the Central Intelligence Agency. Thank you for your service. You've done a lot of different things in your career. How did you originally get started? What sparked your interest in the space program?
That is a great question, because when I was 9 years old, before my brother came home from college, I never thought about becoming an astronaut. So he comes home from college. He was at RIT, Rochester Institute of Technology, and he's looking at my grades, and he's looking at my twin sister grades, and he says, you know, you guys can probably become an astronaut or something like that, because Sally Ride had just been selected. And the way that I was thinking back then was that, oh, they'll never select me. And then next thing he said, well, you know, you can become an aerospace engineer. And so I said, I can do that. I probably can't become an astronaut, but I can become an aerospace engineer. But that was the first time I had anyone say anything like that to me, and that seed to become an engineer started. And it stuck with me from 9 years old all the way through graduate school. So.
That is really cool. So I think the lesson is always listen to your older brother.
Pretty much. Or someone who's wiser than your older brother.
So you mentioned Sally Ride. She gave, the late Sally Ride, she gave one of the more memorable in the series of Hot Science School Talks about 10 years ago. It was, she was really special.
She was a phenomenal lady.
Yeah. So this question comes from someone who calls themselves Curious Student. How many people would it take to land on and explore Mars?
Ooh. That's a really good question. I'll let you start, Dr. Levy.
Sure. The more, the better. No, Curious Student, that's part of the problem is consumables, right? The more people you bring, the more food you have to bring, the more air. If you think about the Apollo program, it was pairs of astronauts that ultimately landed on the lunar surface. My group in Antarctica is usually 4 or 5 people, and we cover a lot of ground. So what sets apart Mars exploration, I think, from Antarctic exploration is the sheer technical expertise that's needed. So how many cross-trained astronauts would you want with you?
So one of the big things that we worry about and we talk about is keeping the astronauts busy and not getting bored or discouraged. And so you would want to have friends come along, and you want to be comrades in everything that you do. So I would want at least 4 or 5 as well. You know, maybe 2 ships come out, one with resources, one with the people. And then as a group together, you kind of can bond and overcome the boredom and different things that you have to psychologically overcome. So I would definitely like the more the merrier.
And Anonymous asks, what social or political challenges will early Martian inhabitants face? No, there's not area of expertise of the scientists and engineers and astronauts, but it's an interesting question.
Let me tell you a story about Antarctica. Sorry, my students are so tired of me saying that. So when the US built South Pole Station in 1958, they were worried about this problem. 60 people at the ends of the Earth, wintering over, no lines of communication. What's going to happen if there's a disagreement? And this disagreement is probably not political. It might be who won the 1954 World Series. So the Antarctic program insisted that a set of encyclopedias be brought in carefully to the South Pole Station to serve as the reference, as the final arbiter. They decided to put it not on the cargo train, but as an airdrop. And it streamed into the ice. It cratered, and the books were lost. And people didn't tear themselves apart that winter, even without a final arbiter in the form of the encyclopedia. So my faith that these astronauts will overcome their social or political concerns locally is high.
I agree, and you know, the closest experience that I have before I go to space has been living underwater for 9 days. And so living underwater for 9 days, I think what kept us going is that we would eat dinner together at night, and we would try to make jokes and make light of the situation. So I would hope that psychologically, emotionally, the people that are selected to go are flexible and adaptable enough to do that. So I would hope that there's no social or political event that could happen that they can't overcome.
And that's really important because it's very likely this mission will be international. Different people from different cultures, from different nations. And I think sitting around the dinner table is the best way to get to know your colleagues and work with them and learn about their differences and celebrate them rather than letting them be obstacles.
And have taco night.
Yes.
Taco night. And tell jokes. That's interesting. So by day 9, was the bar for jokes higher or lower?
Well, it's kind of weird because it was only 9 days, but it flew by. And so I'm not sure how we morphed together. We didn't have any problems. So by the end, when we splashed up from underwater, we were better friends. And I do think that because we're willing to talk about things that happened and open about, things that bothered us, and practicing that as a group, I think that really helped us.
Is this a big part of the astronaut selection process, is being able to pick people who aren't just bright and exceptional in all ways, but can actually just basically get along with others?
That is a huge part of it, but even then, there's no guarantee. So there are times where you really have to practice that, and you just have to focus on being flexible and being very adaptable to whatever situation you're dropped into.
Interesting. So Daniel asks, if one day we do live on Mars, how do I get involved in the architectural design of the research stations and the living quarters and the infrastructure? How does an architect get involved in Mars? Where would they start now?
Well, I can tell you that right now NASA's developing the SLS, the Space Launch System, which is a giant rocket bigger than Saturn V with about close to 9 million pounds of thrust, and on top we'll have an Apollo-like vehicle called the Orion. And we're looking at trying to figure out how to go to the moon, use the moon as an engineering test bed, and a lunar orbiting platform gateway to go deeper and deeper into space. So what I suggest the architect do is continue educating himself through many years of schooling and go work for NASA and try to help build not just a lunar orbiting platform, but a Mars orbiting platform gateway.
Yeah, that key recipe of education and saying yes to science. NASA is staffed by brilliant and brave people, but they're people just like you and me. And so the more you learn, the more capable you are. Just take that risk and apply and find out what internships there are for high schoolers, for college students, for graduate students. At every level, there's some way to contribute. And the more you say yes to those opportunities, the more they open up to you, and that's how you get involved.
Well said.
Cool. So, Joe, this is kind of a follow-up to Jeanette talking about 9 days underwater. DM asks, what was the longest you have been in Antarctica for a research trip? And I'm going to add whether any of these issues we're talking about have come up.
Absolutely, DM. So as a graduate student, I spent 3 months, so 92 days end-to-end in Antarctica, 85 of which were consecutively without a shower because we were out in the field. You wear your funk better than you might imagine. So that you get dropped off in a helicopter with a big box of food. About a month later, they come with more food. A month later, more food, and then at the end of that third month, you get picked up. So it's a long time away from family. It's October to January is the season, so you're missing Thanksgiving and Christmas and New Year's. So the hardest things are just being isolated with these 4 increasingly good friends in a tent camp in the middle of nowhere. And the jokes are key, and the bar gets higher and lower depending on how work is going. But it's a place where you're so busy exploring. I mean, it really is eat, sleep science that the time flies by. And before you know it, that helicopter is coming, and you think, if only I had one more day, I would put off that shower one more day just to get another sample.
Neat to hear. Horatio asks, are astronauts going to need to be vegetarian?
So that's a great question for Mars. That may be the case, but there are resources that are shipped out. And so right now what we have something that's very similar to what the military has, which are these meals ready to eat, where you have food that is packaged. There's meat, there's vegetarian dishes, there's soup, there's desserts. So some of those things can be upmasked to Mars eventually, but over a certain amount of time, Mars will have to become relatively autonomous, as Antarctica becomes. So every now and then you'll get supplies, but you really have to figure out how to live on the land. How do you get water every day? How do you grow things? Can you bring other animals? Can we have a fish pond in one of our habitats on Mars? So these are questions that we're working on answering. Going to the moon as an engineering test bed and learning how to do things on the moon and then transferring that to Mars is one of the big things that NASA has started doing ever since our president said that we're going to refocus our space exploration program to go back to the moon and beyond. So these are great questions, and I encourage every student in here to think about that and think about how you can contribute to the space program.
Very cool. You just answered 3 questions on here about many scientists believe we should go to the moon first as a test bed for getting to Mars. So thanks for being so efficient and anticipating all these questions. Let's take one more question, and it's going to be from, should the question we take be from Finn, or should it be from Geology Boss? Okay, I'll pick. We'll take the question from Finn, because he's had really good questions at previous Hot Science School talks. He asks, would there be a possibility of bringing animals to Mars and somehow building something that could keep them alive?
Yeah. The first explorers to Antarctica ate penguins. I know, they're so cute, and seals. And so there is if you need animal protein as part of your diet, you find a way to do it within a local resource. I sort of love the idea of sheep and goats with little spacesuits on, grazing on the inside. Probably pygmy goats, right? But Antarctica has successfully had greenhouses, and you can, the first explorers said Taylor Valley looked like a good place to grow potatoes. But it's amazing to me that our futuristic civilization is grappling with a Bronze Age problem. How are we going to manage livestock and animals, and where does dinner come from? So no matter how far away we get from Earth, and no matter how advanced our technology, those problems are remaining, and so it's going to require people to be clever and solve them.
I concur 100%.
Any last thing you want to leave our audience with? Any last thoughts? about the future of the space program, perhaps.
I'll start. I guess one of the big things that I hope that Dr. Levy's talk encouraged students to do is to think about Mars and think about how you can solve some of the problems that we'll have in getting there. And it may not happen in my lifetime, but it could definitely happen in one of the youngsters' lifetime, especially if you try to figure out ways to contribute to our bigger question of getting to Mars and then beyond. We're looking at answering questions on this lunar orbiting platform gateway and on the surface of the moon, but we need people to propel us all the way out there. So I just hope that this talk really encouraged you and makes you think about what you can do and how you can contribute.
And we need everyone to contribute. This process, exploring Mars with humans, has begun. You know, there are meetings to select landing sites that future explorers will go to, but it's a long, long way to Mars. And I think the Mars generation is in this room. So I'm so looking forward to helping support you and getting your boot prints on the red planet.
So for all those of you who met Jeanette before the talk and got a picture taken with her, and for all those who've just enjoyed hearing about Joe's hot science, let's really thank them for their time.